Let's study effectively with Miss ICT Skill Builder.
At the very bottom of your hardware, all data is stored as a single bit, a 1 or a 0. Group 4 of those together and you get a 4-bit nibble. Double that and you form an 8-bit byte. When you buy a 1 terabyte hard drive, your computer often reports only 931 gigabytes of available space. This discrepancy means nearly 70 gigabytes of capacity appear to vanish as soon as the drive is plugged in. Because individual bytes are microscopic, we measure modern storage using massive multipliers. At this scale, the mathematical standards used by hardware manufacturers begin to clash with the standards used by software. Hardware manufacturers calculate space using the commercial SI system, which operates in base 10. Under this standard, multipliers are clean thousands. 1 kilobyte is exactly 1,000 bytes, and 1 megabyte is exactly 1 million. This table shows the internal base 2 standard your computer uses, laid out by the IEC. Because it scales in powers of 2, the multiplier is 1024. 1 kibibyte is 1,024 bytes, and 1 megabyte is 1,024 kibibytes. It takes more individual bytes to reach each threshold on this ladder. This gap in reported space exists because operating systems calculate capacity using these base 2 logic units, while hardware is marketed and sold using base 10 units. We can calculate exactly how much space a single file occupies using these base 2 rules. For an uncompressed raw image, we multiply the total number of pixels by the color depth. A 1,000 by 1,000 pixel image with an 8-bit color depth requires 8 million bits. To make this number useful for storage, we have to group those raw zeros and ones into standard bytes. Dividing that total by 8 gives us exactly 1 million bytes. To find the final file size in megabytes, we scale up the IEC ladder. We divide the byte count by 1024 to find kibibytes, and then divide by 1024 a second time to reach 0.95 megabytes. Calculating data capacity follows a strict linear path. You isolate the raw data points first, group them into bytes, and only scale up to the larger IEC multiples at the end. Sound files use a similar progression. We multiply the sample rate by the sample resolution, and then by the length of the track in seconds. For a 60-second clip recorded at 44.1 kilohertz and 16 bits, the result is 42,336,000 bits. If this recording is a stereo track, it uses 2 channels. This means the entire bit count must be multiplied by 2 to account for the additional stream of data. We then apply the conversion ladder once more, dividing the total bits by 8, then by 1024, and 1024 again, reveals a final file size of 10.1 megabytes. Accurate calculations require more than just math. They require an understanding of the physical properties of the media, like the number of channels being used. At 10 megabytes per minute, a standard hour-long recording would require over 600 megabytes of storage. As media files grow in resolution and length, uncompressed data quickly fills local hard drives. Transferring these large files also consumes network bandwidth, the maximum rate at which data moves. Large uncompressed files take longer to upload and download, and often lead to higher costs for cloud storage and internet service. Compression reduces the number of bits in a file, which lowers the bandwidth required for transmission. By shrinking the data, files can move across a network faster while staying within the storage limits of a device or a cloud account. Lossy compression reduces file sizes by permanently deleting unnecessary data. In an MP3 file, the algorithm uses perceptual music shaping to identify and remove sounds that the human ear cannot hear, such as frequencies outside our hearing range. While this works for media, deleting data is catastrophic for spreadsheets or computer applications. These files require a method that can reduce the size without losing a single bit of information. Lossless compression, like run-length encoding, solves this by mathematically grouping repeating data. Instead of storing 10 individual colored squares, the algorithm stores a single code representing the count and the color, which can be perfectly reversed later. This creates a fundamental rule. Lossy is used for media like JPEGs and MP3s, where human perception won't notice the missing details. Lossless is used for text and code, where every character must be perfectly reconstructed. By matching the right compression algorithm to the specific type of data, we can maintain the integrity of our files while ensuring they transfer and store as efficiently as possible.
Thanks for watching. If this helped you clear up the concept, hit that like button and share it with a friend who might be struggling with it too. Let's build those skills together.